So now what I'm going to show you is the notion of witness indistinguishable proofs, which is a remarkable notion. It's a relaxation of zero knowledge that is very meaningful and very appealing. And I'll show you how to use that to get statistical zero knowledge arguments for NP, which is sort of the dual of what we've been seeing so far. And I just want, as a teaser, to tell you that what I'm going to show you in this lecture is what I call the mother of all zero knowledge protocols. Okay, this is the ultimate zero knowledge protocol, what you're going to see. It has everything. If you can grasp all the ideas in these protocols, you understand zero knowledge. Okay, so it's worth listening. It's an amazing protocol, really remarkable paper. Okay, so let's again get onto it. So we call the definition of statistical zero knowledge, which is a relaxation, a slight relaxation of perfect zero knowledge. It requires that the simulator's output is statistically close to the real interaction. And you'll see occasionally I'll have the witness being as auxiliary input to the prover and the auxiliary input Z as being auxiliary input to the verifier, and sometimes I will omit it just so that I don't overload your eyes too much. But it's always with auxiliary inputs to the prover and verifier. And we saw that a perfect zero knowledge is contained in statistical zero knowledge, contained in computational zero knowledge. And we saw that we cannot hope to prove NP languages in statistical zero knowledge, because if we could, then the polynomial hierarchy would collapse. And we said that we had two possible relaxations, one of which we already saw. The first relaxation is to make computational zero knowledge, to make the simulation computationally indistinguishable. And the other relaxation, which we'll be focusing now on, is computational soundness, meaning that we will require the simulation to be statistical, but the soundness will require it to hold only against computationally bounded provers instead of arbitrary provers. So this brings us to the definition of arguments, which, by the way, appeared very shortly after the Goldwasser-Mikhaili-Rakov paper and the Goldreich-Mikhaili-Wigderson paper by Brassard, Chow, and Crépeau. And they define an interactive argument system as opposed to proof for a language L. They require the following two properties. One is completeness. It's as usual. Okay? Perfect completeness. If X is in the language, then the prover always convinces the verifier. The relaxation here is in the soundness property. It says it requires that if X is not in the language, then for every probabilistic polynomial cheating prover P star, and the relaxation is here, that we quantify only over polynomial time provers, the probability that the prover makes V accept is negligible in some security parameter N. And typically, this computational soundness is based on a cryptographic assumption. One very prevalent assumption in these cases is collision-resistant hashing. Okay, so assuming the hash function that we use in the protocol is collision-resistant, the polynomial time prover will not be able to break the soundwares, or else will find collisions in the hash function. And the security parameterizes how hard it is to break the assumption. Okay, so here it's not just a matter of how sound the protocol is, like 2 to the minus k, but there's also this issue of quantifying over the hardness of the security assumption that underlies the computational soundness. And one interesting thing to note, which we'll not dwell about, is that whereas in proofs, if you repeat k times in parallel, the soundness goes down accordingly, exponential with the number of repetition. This is not necessarily true for arguments. There exist arguments so that if you repeat them in parallel, the soundness doesn't go down. And the issue is malleability again. We will not talk about it further. For 3-round arguments, the soundness does go exponentially fast, but not as fast as you would expect, at least not according to the best analysis that we have. But for 4-round protocols and up, there exists protocol where the soundness doesn't go down. So you have to be careful with arguments when you're repeating them. Typically what you do, you design them to begin with negligible soundness. Okay, you don't design them with constant soundness and then repeat, because then you might run into trouble, unless you're very careful. Okay, so let me say a few words about computational zero-knowledge proofs versus statistical zero-knowledge arguments. So in computational zero-knowledge proof, the soundness is unconditional. which is awesome. It means that if you pass verification, there's no chance that the statement is false. Really small chance. You cannot dispute the veracity of an accepting statement. On the other hand, what you pay, the price that you pay is that the secrecy or the zero-knowledge property is computational, meaning that even though right now the transcript doesn't reveal anything beyond the fact that X is in the language, maybe sometime in the future it will, if the computational assumption is broken. There is the risk. Statistical zero-knowledge arguments, on the other hand, are the dual of this. The secrecy is unconditional. It's statistical. It means that once the run of the execution is over and the transcript is out there, there's statistically no information about the secrets that you want to reveal. So it's excellent. They have no worry in the long term. On the other hand, the soundness is computational, meaning that even though you pass verification, you always have the lingering doubt that the computational assumption was broken by this super powerful prover, and it's actually not a true statement. Now, one has to be careful here. So sometimes people argue that arguments are much better because when you interact with the prover, he has very little time to respond, right? It doesn't take forever to break the assumption and to respond. So maybe it's a preferable notion because, if within 1 second he didn't break the assumption, then the protocol was sound. It's true, in principle, at least at a philosophical level, but you have to remember that sometimes people use arguments in long-term settings where there's a common trusted setup or something that lives there for a very long time. And if that gets broken in the long term, then it's a totally different setting. So you have to be careful when you argue these meta-philosophical things. Okay, 7 more minutes. So let's see, first of all, let's see how NP is contained in SZK arguments with constant error. So the theorem, if statistically hiding commitment exists, then there is an SZK argument for Hamiltonicity. Computationally sound and statistically secure. The protocol is the same protocol that we saw. The only difference is what? That the commitment that we use here is statistically hiding and computationally binding. It means that a computationally bounded prover cannot break the binding, and an all-powerful distinguisher cannot distinguish the output of the simulator from the real interaction. So this is the claim. I'm going to skip it. It's the same argument as we have before, except that now you have 2 cases. Either U and pi of G are consistent, in which case you get a cycle in the original graph, or they're inconsistent, in which case you broke the computational binding of the commitment. I'll let you think about it offline. And statistical zero knowledge follows from the fact that when you commit with a statistically hiding commitment, these are statistically close. Okay, so you extend the argument we had in the previous lecture on zero knowledge proofs for NP, and you argue that the output of the simulator is statistically indistinguishable from the real simulation. Now, that's very nice. We have a constant, a soundness error, statistical, zero knowledge argument for NP, but the problem is that the soundness is constant. So we want to amplify soundness. We already saw that we have 2 methods. One is sequential repetition. It results in negligible soundness, but higher round complexity. We have parallel repetition. It should result in negligible soundness. Luckily for us, this is a 3-round protocol, so it could in principle, but we have to be careful about it. And it has low round complexity. This is indeed the zero knowledge. It follows from the fact that each atomic component is auxiliary input zero knowledge. We talked about this in the first lecture. This one, not clear. Enter the notion of witness indistinguishability. I'll give you the definition and then we'll go out for a break. I'll leave you to think about the definition. So remember, our goal is to use witness indistinguishability to construct an argument for every language in NP that is statistical zero knowledge, has negligible soundness, and is constant round. All these nice features. It's the dual of the previous result that we saw. And the main tool is witness indistinguishability. What is witness indistinguishability? It's an extremely useful and also very meaningful relaxation of zero knowledge. It's a security property of protocols. It's weaker than zero knowledge, but very interesting in some cases. And the requirement, if I can say it in word, is that the interaction between the prover and the verifier does not reveal which of the possible NP witnesses was used. Just like encryption doesn't reveal which message was encrypted. Same idea. It might leak other information, but which witness was used is not revealed. So witness indistinguishability says at a high level, we'll define it formally in the next slide, for any two possible witnesses, NP witnesses, for any two possible proofs for the NP statement, the transcripts, when the prover uses W1 to prove, is computationally indistinguishable from the transcript when the prover uses W2. The interaction does not reveal which of the two witnesses were used, even if the witnesses are known, by the way. Remember, we were talking about this when we were talking about commitment. Another notion which is stronger, we call it witness independent. It's the same, just with statistical instead of computational. So the distributions of the two interactions are statistically close. Now, this is defined, when I say witness for X, what do I mean? For this statement to be even remotely meaningful, I need to define an NP relation. So let's talk about an NP relation. So an alternative definition of NP, of a language in NP, so a language is NP if there exists a polynomial time recognizable relation so that X is in the language, if and only if there is a witness, so the pair X, W is in the relation. What do I mean by polytime recognizable? It means that given X and W, I can decide if they belong to the relation or not. So you can, for any X in the language, and given a relation RL, you can define RL of X, which is a set of all possible witnesses for X. So you can, alternatively, this is all the W's such that V of XW is accept. Which hints that implicitly, the NP relation is totally determined by the NP verifier that we talk about. Fix an NP verifier defines the NP relation. Two things I want to point out. One I already did, that the relation is fully determined by the verifier. And the other one, which is sometimes overlooked by people, is that every language in NP has infinitely many relations. Okay? You can always augment the relation, the witnesses, with some dummy bits that has no relevance to whether X belongs to language or not. So it's really important to fix which relation we're talking about. And this is important when you design protocols that use WI. It has to be with respect to a fixed relation. And this is sort of like saying, guys, this is the information I want to hide. The NP relation specified what's the information you want to hide about the witness. Okay, this is our way of saying this is the information I'm hiding. Yes? How can I define a bad relation? Yeah, so for instance, if your NP relation for factorization is P comma Q, as opposed to some other relation, then you reveal the factorization, and it's not necessarily a hard language anymore, and you reveal something that is hard to compute otherwise. Okay, so let's go over the definitions. So an interactive proof is witness indistinguishable with respect to R sub L, the NP relation of sub L, if for any polynomial verifier V star, and for every X, and for every two witnesses, possible witnesses for X, W1, W2, in RLX, the two transcripts are indistinguishable. Whether you use W1 or W2 is indistinguishable. And I want to point out something that some of you might have thought about, is that if there's a unique witness, then witness indistinguishability holds trivially, right? Because there's in a vacuous way, which means that sending the witness is a witness indistinguishable protocol. And it's clearly not a secure protocol, okay? So witness indistinguishability is interesting whenever you have more than one witness. And you have to design things so that you have more than one witness. And again, I emphasize that this is interesting even if the witnesses are known, are public and known. Okay? Just like encryption. Encryption could be hard to break even though you know that the encryptor might encrypt either buy or sell. Okay? It should still be hard to break. Same idea. No different than that. And here's how the two points for thought for the break. Every zero-knowledge proof is also witness indistinguishable. We will argue that. And more importantly, unlike zero-knowledge, witness indistinguishability is closed under parallel composition. So now we're about to embark into the most beautiful protocol ever, until you see the one that I'll show you tomorrow. So let's recall. So we defined witness indistinguishability. We said an interactive proof is witness indistinguishable if it doesn't reveal which one of the possible witnesses for X in the language was actually used by the prover. And we said it's interesting only if there's more than one witness, otherwise it guarantees nothing, right? Because we said a proof where you send the witness is witness indistinguishable vacuously, and it's clearly not secure. And we said that it holds even if the witnesses are public, just like encryption. And we had these two observations that will be very useful for us. That on the one hand, every zero-knowledge proof or argument is also witness indistinguishable, and that the notion of witness indistinguishability is closed under parallel repetition. Unlike zero-knowledge, for which we don't know if this is the case. Before we continue, I want to give you as food for thought an equivalent definition to witness indistinguishability, and this is the notion of unbounded simulation. What is unbounded simulation? I just require that the view of any polynomial time verifier can be simulated by some function, not necessarily polynomial time. Okay, so for every V star, there's an S, not necessarily polynomial time, that simulates in a computational indistinguishable way the transcript. So, or in words, a protocol has unbounded simulation, and whatever a polynomial time verifier could have learned for the protocol, it could have learned in exponential time. It sounds a bit like a bizarre notion, because we're giving the simulator much more power, but it is very interesting, especially in settings of secure computation and such. We'll not get into it, but sometimes it's interesting even to show unbounded simulation. The first claim is that a protocol has unbounded simulation if and only if it's WI. The first direction is that if it has unbounded simulation, it is WI, and the way this is proved is by noticing that on the one hand, the simulator is indistinguishable from an interaction where the prover uses W1, and on the other hand, it's indistinguishable from interaction where it uses W2, so by transitivity, these two are indistinguishable. So this implies witness indistinguishability. This argument works even if the simulator runs in exponential time or unbounded. In the other direction, I'll leave it an exercise. I'll leave you as an exercise. Try to think why, if it's WI, then it also has unbounded simulation. Hint, try to think how long it would take to find the witness. Okay. Now the claim that I claimed before, if a proof is zero knowledge, then it is also witness indistinguishable, and here is the proof. If it's zero knowledge, then it has even an efficient simulator. So it's an even stronger statement than we had before. And again, the same argument implies witness indistinguishability. Just put the simulated transcript in between the two executions. And by transitivity, they're indistinguishable. So what's the corollary of this claim? If statistically binding commitment exists, then every language in NP has a witness indistinguishable proof. And the proof for it is just take the computational zero knowledge proof for Miltonicity. Since it's zero knowledge, it's also WI, and that's it. Another corollary, which is the dual of this, is that if statistically hiding commitment exists, then every language in NP has a witness-independent proof. Just take the dual of the Hamiltonicity protocol where we use statistically hiding commitment instead of binding. So every language in NP has a constant round witness indistinguishable proof and a constant round witness indistinguishable argument. Another property that is nice about witness indistinguishability is that it's closed under parallel composition. And let's P to the K, V to the K denote K-fold parallel composition. And the theorem is that if a single execution is WI, then K repetitions in parallel are also WI. And the way this is proved is using a hybrid argument. The good old hybrid argument, and remember that we allow W1 and W2 to be known. Witness indistinguishability holds even if we know the witnesses. So you start with a proof, K repetition with a proof that use W1. So you have, these are the repetition. I just show you the witness that is being used in each one of the repetition. Then you switch to K repetition with the first witness in W2 and all the rest are W1, and so on. You do the hybrid argument, and by the end of this process, I hope it will not take too long, you end out with the K repetitions where you only use W2. So composition is really easy with witness indistinguishability using a hybrid argument. Yes. It doesn't have to be polynomial, but typically we take it to be polynomial. So the theorem is that, assuming non-interactive statistically binding commitments, every language is NP has a 3-round witness indistinguishable proof with the soundness error 2 to the minus k. And in fact, this is a proof of knowledge, like Yuda showed, with knowledge error 2 to the minus k. It's not a strong proof of knowledge, but it is a proof of knowledge. The other theorem is that if we have 2-round statistically hiding commitments, remember that statistically hiding commitments require this extra round, where the receiver sends CRH, or we need the G and H to be sent to be set. So assuming 2-round statistically hiding commitments, every language in NP has a 4-round witness-independent argument with soundness error that is exponential in minus order k. Why do I say exponential in minus order k? Because the soundness error goes down exponentially, but not as fast as you'd expect. But it's still exponentially small in k. So we have 3-round witness indistinguishable proofs and 4-round witness independent arguments.
Is there a non-interactive statistically binding commitment that is not perfectly binding?
I don't know. Okay. And the protocols are in fact proofs of knowledge. And what we'll do, we'll use them now to construct the mother of all protocols, a 5-round statistical zero knowledge argument of knowledge for NP. And as an application, we'll have a constant round identification scheme according to the blueprint I gave you at the beginning of the first lecture. And also Yuda gave it at the end of his lecture. And both will have exponentially small soundness error. Okay, so let's get to it. Constant round SZK arguments for NP with negligible soundness error. So the prover holds a witness W for the statement X is in the language. And we assume we have a one-way function F. Okay, so we all agree that F is a one-way function. It's agreed by everybody. Here's what the verifier does. He picks 2 inputs to the one-way function. Let's call them Z0, Z1. He picks them at random. And he sends the following pair. He sends Y0, Y1, which are equal to the pair F of Z0 concatenated with F of Z1. So it's 2 images of a one-way function. Now, if you get Y0, Y1, and you define the language whose witnesses are Z0 or Z1, like a pre-image of 1 of Y0, Y1, first of all, notice that this language it's hard for this to find a witness for this language on the average, right? Because it's hard to invert the one-way function. And also, every instance of this type has more than one witness. It's either Z0 or Z1. So it's an artificial way to generate a hard on the average instance that has more than one possible witness. Okay, so that's the idea of this message. And now the prover and verifier engage in the witness indistinguishable proof of knowledge of a statement that I'll define in a second. Once they're done with it, they engage in a witness-independent argument of knowledge. I want to point out the subtlety here. You see here is WIPOK, and this is WIAOK. When I say WIPOK, I mean indistinguishable proof. When I say IA, I mean independent argument. Okay? So this is the difference between the two, the duals of each other that we talked about. What is the statement, the NP statement that is being proved in the witness indistinguishable proof? Is that there exists a Z, so that either Z is a preimage of Y0 under the one-way function, or Z is a preimage of Y1. So this is our NP relation. It's hard on the average to find a witness, and there is more than one witness for every instance. What's the NP statement proved in the other direction? And here is a very shrewd and beautiful idea coming into play. The prover proves that either X is in the language, meaning that there exists a witness for XW being in the relation, or he knows a Z that is a pre-image of Y0, or he knows a Z that is a pre-image of Y1. So there are two ways to satisfy, actually three ways to satisfy this relation. Either you find a witness for X and use it in the proof, or you find a pre-image for Y0, or you find a pre-image for Y1. And remember that we're proving this, keep in mind that we're proving this with a witness-independent proof of knowledge. So whether I use W or Z will be indistinguishable to the verifier. Okay, so keep this in mind, we'll of course use it. Now the protocol is constant round, because each of its components is a constant round. The first component is 3 message, the second component is 4 message. So it's all fine in terms of constant round. And notice that these are NP statements. Okay, this is something that we need to use. Why is it important? Because when we prove a double witness indistinguishable proof of knowledge, we use the fact that the statement that we're proving is in NP, and we said that there exists such a witness indistinguishable proof of knowledge. The arrows indicate in which direction the proof goes, by the way. So this goes from the verifier to the prover, and this goes from the prover to the verifier. So for completeness, the first thing that the prover does, he verifies that the proof that he is on the receiving end of is accepting. And then he uses the witness that he has to prove this statement. By completeness of the witness-independent argument of knowledge, you can do that. You can use this rule. So completeness is easy. If you have a witness, you can pass verification. And now the verifier accepts, and everybody's happy. What about soundness or proof of knowledge? Now we have a cheating prover, P star, and X is not in the language. So this means that this is, by definition, false. The only way to convince is either to prove that you know a preimage of the Y0 or a preimage of Y1, right? Because X is not in the language. So here's what you do. You want to say that a computationally bounded prover, P star, cannot cheat in this case. So what we're going to do, we're going to use all the properties of the protocols, essentially, to show that we can use this cheating prover to invert the one-way function. How do we do that? We get from outside an image of the one-way function. Let's call it Y sub B for a random B. So it's f of Z sub B. Okay? So we only know Y, we don't know Z. We sample ourselves the other output of the function. Let's call it Y sub 1 minus B. So it's f of Z1 minus B. And we do know this one. We don't know this one. We do know this one. And this just denotes that we shuffle the two randomly. We decide which one of the two to send. We use the preimage that we know to prove that we know either a preimage of this or of this, depending on B. We managed to do this because of the completeness of the protocol. And we now verify this proof and extract a witness for this statement. What is a witness for this statement? A witness for this statement is a preimage of either Y0 or of Y1. Why? Because it cannot be a witness for this because it doesn't exist. So we extracted some preimage of the one-way function, and the question is whether we extracted our own preimage, which gave us nothing, or we extracted the one that we didn't know, one of the two. And what we want to claim is that since this protocol is witness indistinguishable, an efficient prover cannot guess which one we don't know, cannot guess B. Okay, so if he could guess B with some noticeable advantage over 1/2, we could use him to break the witness indistinguishability of the first protocol. So here is the claim. If the proof of knowledge, the first one, is witness indistinguishability, then for any efficient prover P star, the probability that what we extract gives us nothing is Y sub B is the, no, not gives us nothing, gives us the preimage that we don't know, is roughly 1/2. And I leave you as an exercise to prove that otherwise, you can use P star to distinguish between whether we use Z sub B or Z1 minus B. So this is based on the witness indistinguishability of the first component. Good, so if with probability 1/2 we got Z sub B in the extraction, notice that this gives us a preimage of Y sub B. So we inverted the one-way function. So if P cheats with probability epsilon, we inverse the one-way function probability epsilon over 2, roughly. Otherwise, we could distinguish between one proof or the other. Now, all of this maneuver, I'm hand-waving here and I'm making it look modular and simple. There is something to do, but I have to say that this is much easier to argue than typical zero-knowledge protocols. Okay, so in terms of a proof, it's a pretty clean proof if you have to write it down as an exercise. So if F is one way, then P star makes us accept X not in the language with negligible probability, which we wanted, what we wanted to show. This is, it has negligible soundness error. Okay, so now we proved that it's complete and it's sound. Let's see why it's a zero-knowledge argument, statistical zero-knowledge argument. So now let's think of the simulator as playing the role of the prover for X in the language, but the simulator doesn't know a witness for X. You'll have to find some way to cheat the verifier without knowing the witness. So what will the simulator do? It will use the fact that the first protocol is a proof of knowledge. It will extract Z, right? Because if verification passes, it extracts Z. What does the simulator do if verification doesn't pass? It just outputs garbage. It says, you know what, I'm not willing to engage in these interactions with you. This is what you get. Okay, so we assume that there's some probability with which the verification passes, and then we can extract the preimage. And once the simulator has a preimage, what does it do? It uses D to cheat in this part. It uses G either for Y0 or phi1 of Y1. And why this will result in a good simulation that is indistinguishable from the real interaction? Because the second part is witness independent. Not only that it's indistinguishable, it's statistically indistinguishable. You cannot distinguish whether you use the first item, the second item, or the third item because of witness independence. So now the simulation is statistically close to a real interaction. So the claim is that if the argument of knowledge, the second one, is witness independent, then for any polynomial time V star, the simulation is statistically close to the real interaction. And I leave you as an exercise to prove it. Here are the hints and the details. It's actually, if you have time this evening in Jaffa, it's highly recommended. Okay, so here's a corollary. If two round statistically hiding commitments exist, then every language in NP has a constant round statistical zero-knowledge argument. Beautiful protocol. It uses all moving parts that you can think of, combines them together in a perfect way, and gets a wonderful result. This is a protocol by Feige Shamir, by the way. It's one of the best protocol papers ever. Okay, but this protocol, the way I described it, doesn't have 4 rounds, and this is what we could hope to aim for. Remember that proofs can be built in 5 rounds. We saw that 4-round proofs are impossible. Could we hope to get 4 rounds argument if we're really trying to optimize the round complexity to the minimum? So we have, what do we have here? We have a first message. Then we have 3 messages of the witness indistinguishable proof of knowledge. And then we have 4 messages of the witness indistinguishable argument of knowledge. How do we get from these to 4 rounds? Here's a suggestion. We piggyback the messages one over each other, okay? So we notice that the first message is independent of the statement. So it certainly can correspond to both of these first messages. And then we carry on and we get a total of 4 rounds. Except that, so this is the 4 round, except that it doesn't work. At least on the face of it. And the issue is very subtle, is that when you simulate, you extract from this witness indistinguishable proof of knowledge, and you need to set the second message here in order to cheat in the simulation before you have extracted the fake witness Z here. So you have to be really careful about this. This is something I noticed while I was preparing the slides. I was convinced it works, and then it didn't work. I'm not convinced that one cannot make a careful argument that it works. It might be worth thinking about because this is a very elegant protocol. In any case, it's possible to get 4 rounds in a different way. Yes? The problem that I see, it might not be a problem for all I know, is that when the simulator extracts, it needs the third message here. And then this message will depend on the witness that you extract, and this happens before this. Now, my intuition is maybe that you can extract and set this message after you've extracted. That might be possible, but I haven't thought this through, so I don't want to claim it. In any case, you can do it in a different way. There's a paper by Bellare, Jacobson, and Jung from '97, where they show that you can get 4 round arguments from any one function. Feige and Shamir show it based on discrete log, on a specific assumption. And the interesting technique by Bellare, Jacobson, and Jung, I think they use garbled circuits or something related, which is interesting in the context of zero knowledge. One central tool that is used, which is interesting just to mention, is the notion of trapdoor commitments. I already sort of mentioned it when I talked about Pedersen commitments. So you have this commitment of the form h to the r times g to the m, and I told you that if you know the discrete log of h to the base of g, then you can open in any way you want. This is one of the tools that is being used for 4-round arguments. And another tool that is being used that we're about to talk, yeah, we have time, good, is the notion of witness hiding. What is witness hiding? It's yet another relaxation of zero knowledge. Whereas witness indistinguishability says you cannot distinguish which witness was used, witness hiding said that the interaction doesn't allow us to extract the witness. It might leak information on the witness, but the whole witness is not revealed. Okay, so let's summarize so far before we move on to witness hiding. So we defined interactive arguments. We talked about statistically hiding commitments. We talked about witness indistinguishability and independence. And we saw that every language in NP can be argued in statistical zero knowledge. We saw that zero knowledge imply WI, and hence NP is provable in WI, and that you can reduce soundness by composing in parallel of WI. So it's amazing. You start with a zero knowledge protocol. An atomic one implies WI, and now you repeat many times and you get a WI with negligible soundness, and using a hybrid argument. And then we saw the Feige-Shamir protocol, the mother of all protocols. Okay. Witness hiding. So to motivate witness hiding, I don't want to get too technical into this. Let's look into the application. So here is what we talked about in the first lecture today, is how to use zero knowledge to build an identification scheme. Okay? So Alice wants to publish some public information for which only she knows the secret, and then she's going to prove to Bob that she knows the secret, and she's going to do it in zero knowledge so that later Bob cannot impersonate her, because it was zero knowledge. It only convinced Bob that she knows the secret. So in the setup phase, we have a secret generation algorithm. Let's call it gen. It gets a security parameter as input. And Alice picks a preimage of a one-way function, a random input to a one-way function, and publishes y equals f of z. So given y, it's infeasible on the average to find z, even though Alice knows the solution. And now at the identification phase, given that y is public, Alice used the zero knowledge proof of knowledge to prove that she knows the preimage of f. She knows a z such that y equals f of z. This is an NP statement. We can do it in zero knowledge, assuming one-way functions. And the claim is B star, Bob, star cannot impersonate Alice. And it's useful to look at this example because it's a classical use of zero knowledge proofs. This is how zero knowledge proofs are being used. Suppose Bob, B star, can impersonate Alice to Charlie. How does he do it? He claims, I'm Alice. I know the preimage of Alice as y. And then, suppose he can do it by proving a zero knowledge proof of knowledge of the preimage of y. So here how the proof works. Since the left interaction is zero knowledge, we can simulate it. So whatever Bob could have done given the proof on the left, he could have done without the proof on the left, right? Just run the simulator and generate the distribution of messages on your own. Now, on the right, since it's a proof of knowledge, you extract a witness. And now you have this machine that gets, as input on the left, it gets y equals f of z. And out of thin air, it extracts the pre-image of y. So if Bob could impersonate Alice in this protocol, we could have used him to invert a one-way function by simulating on the left and extracting on the right. So this is the classic use of zero-knowledge proofs of knowledge. So this is one way to think of zero-knowledge. Think of zero-knowledge as just an efficient reduction. You say, if Bob could break my protocol, I have a reduction to break the underlying assumption. So zero-knowledge is a reduction, a clever reduction. Just masked in a very fancy definition. And we can use a constant round zero-knowledge proof of knowledge with negligible error, which we already saw that it's pretty nasty. Takes 5 rounds, needs statistically hiding commitment, and so on. And here is the observation by Feige and Shamir. Witness hiding is enough for this. Meaning, I don't really need to be able to simulate this view on the left in a way that reveals nothing. All I need not to reveal is what? The pre-image of y. Remember when we tried to define zero-knowledge, we said maybe all we want to hide is the witness. Maybe it's good enough, and I told you it's good enough for application. Here is an application where this is good enough. There's no need for zero-knowledge here. And the same applies for signatures. Okay? Zero-knowledge is an overkill. Remember this, because if you're ever going to design an efficient protocol, you might as well do away without zero-knowledge, which is a very demanding requirement. Okay, so let's let's build an identification scheme with our notion of witness hiding. And then we'll define witness hiding. Okay, we'll first see a protocol, and then we'll define witness hiding. So Alice, instead of picking 1z and prove that she knows the pre-image, she will pick this instance that we know from before, y0, y1, with 2 possible pre-images. And when she identifies, she proves in a witness indistinguishable manner that she knows a pre-image either of y0 or of y1. And the statement is this. She knows there exists a z, so that either f of z equals y0 or f of z equals y1. And we already saw in the Feige-Shamir protocol before that if the proof is witness indistinguishable and f is a one-way function, then B star cannot output z, follow the interaction. We already used it in the previous protocol, in the soundness of the previous protocol. It was implicit in our argument. Witness indistinguishable proof of this statement does not facilitate finding the pre-image of the one-way function. Which brings us to witness hiding. Essentially, that protocol that we just saw is a witness hiding proof of this statement. So what does witness hiding mean at a high level? It means the following. If V star can output a witness following the interaction, he could have done so without the interaction. That's what he said. It's a weakening of zero knowledge. It's in the same spirit, right? Zero knowledge is, we say, whatever V star could have done with the interaction, he could have done without it. Here we're focusing on a specific task that he could have done without. It's just finding the witness. Witness hiding is certainly implied by zero knowledge, but not necessarily implies zero knowledge. It might be, for instance, I might be able, following the interaction, to output the first bit of the witness, but still not be able to output the entire witness. And this is not zero knowledge, but it is witness hiding. And you have to define it carefully because it has to be hard to find the witness. So you need this instance generator. We saw an example of an instance generator. I don't want to get into these kind of details. Here's the definition. The definition is the proof is witness hiding with respect to a generator and a relation, an NP relation, if there exists a machine M, so that for every verifier, the machine M succeeds almost as good in outputting the witness, almost as good as it could have done given the transcript If it can extract a witness given the transcript, it could have done equally well without the transcript. This is what this equation says. We might as well just focus on the first sentences. That's just a formalization of what we said here. If you could extract a witness following the interaction, you could have done without it. And the claim by Feige-Shamir is that if an NP statement has two independent witnesses, then any witness indistinguishable protocol for X is also witness hiding. So witness indistinguishability implies witness hiding if you have more than one witness. Okay, so let's use witness hiding. We're getting close to the end. Let's use witness hiding to show that Bob cannot impersonate Alice. So here we have the statement generated by the generator. Here we have a witness hiding proof of knowledge, and here we have this cheating Bob. Bob tries to convince Charlie using a witness hiding proof of knowledge. If you can extract following the interaction from Bob, then you could extract without the interaction. That's what the definition of witness hiding says. If you could have extracted with the interaction, you could have extracted without the interaction. So by witness hiding, this machine that we had in the definition output a witness for y0, y1, inverting the one-way function. I leave it as an exercise. Okay, so what is this good for? Interestingly, even before witness indistinguishability and witness hiding were introduced, there was a protocol. Sounds familiar? It's called the Fiat-Shamir protocol. Most of you might have heard the combination of words Fiat-Shamir. So it originates from this idea. So they took the quadratic residuosity zero-knowledge proof. They repeated it in parallel k times. This is Fiat-Shamir. It's before they had witness indistinguishability. Okay? A single execution is zero knowledge and also WI. This is the reasoning why it's secure, the Fiat-Shamir identification. A single execution is WI, so K executions, parallel execution of WI. So we have now a witness indistinguishable proof for quadratic residuosity with negligible soundness. Soundness 2 to the minus K. Since there are multiple witnesses to a quadratic residue, then it's also witness hiding. And this gives an identification scheme that is based on hardness of finding a square root, modular composite, using exactly this very same analysis. There's a recent, very exciting line of works. Maybe Ron will tell us about it tomorrow, I'm not sure. Quite remarkable, showing how under cryptographic assumptions you can make this protocol non-interactive, which in particular means that even though it's witness hiding, it is not zero knowledge. We'll talk about it tomorrow morning and afternoon. It's been open since then, essentially. Okay, how much time do we have? I want to show you one practical protocol, one practical identification protocol, which is well known. It's used in practice, almost used in practice, and maybe Benny will talk about it when he talks about Sigma protocol. It's Okamoto's identification protocol. And I want to try and show you how this protocol falls into the template of what we've been seeing so far. So in Okamoto's protocol, we use this Pedersen commitment idea, h to the z0 times g to the z1. So we have a commitment to z0 using randomness z1, if you think about it this way. So you have a statement y with multiple witnesses. And the protocol is just a proof of knowledge of either z0 or z1. And the protocol goes as follows. You send h to the r0 times g to the r1. You get a challenge s. S is a random element in C sub q. It's a very long element. The challenge is long, and the soundness is negligible. It's 1 over q. And then you give one of two answers and verify something in the exponent. Doesn't matter the detail. What I want to point out about this protocol is that it's witness independent with soundness error 1 over q. And each y has q witnesses. Q pairs will attest to y. So you have multiple witnesses. It's witness independent, so protocol is witness hiding from the reasoning that we have. And this makes this an instantiation of the identification scheme that we talked about without repeating many times in parallel and with negligible soundness in one shot. Okay, and this is how you get efficient protocols. Okay, you don't repeat many protocols in parallel, but you use these so-called sigma protocols. Okay, so let's summarize. What did we do? We defined interactive arguments. We talked about statistically hiding commitness, with indistinguishability, independence. We talked now about the notion of witness hiding. What we saw is that every language in NP can be proved in statistical zero knowledge if the prover is computationally bounded. We saw that zero knowledge implies witness indistinguishability, and witness indistinguishability composes in parallel. That's the important part. That NP can be proved in statistical zero knowledge in a constant number of rounds, not proved, argued in statistical zero knowledge in a constant number of rounds. And we saw identification schemes both using zero knowledge and using this weaker notion of witness hiding. Some food for thought to conclude my lectures for today. Here's one food for thought. So when we analyzed the security of the identification scheme, we assumed that the zero knowledge proof of knowledge here on the right-hand side takes place after this is completed. But what if they take place in the same time? Now, even though the left proof of knowledge is zero knowledge, security is not guaranteed anymore, because it falls outside of our model of an attacker of zero knowledge. Okay? If you try to carry out the proof, it will fail. You will not be able to simulate on the left. And this is a real attack. We talked about malleability attacks. You can attack the Okamoto scheme. The Okamoto, actually, I'm not sure you can attack. It's an amazing identification scheme. But you can attack analogous identification schemes using a man-in-the-middle attack. And again, you have to be aware of this. These are devastating attacks. So this is a real-life concern. Another point for thought. So I want to make an analogy between zero knowledge and semantically secure encryption, and between witnessing indistinguishability and the indistinguishability of encryption. As some of you might recall, we have two definitions, two equivalent definitions of security for encryption. One is indistinguishability of encryption, meaning that you cannot distinguish whether I encrypted one message or the other. And the other one is semantic security, which has a simulation flavor. It says whatever I could compute, whatever function of the plaintext I could compute from the ciphertext, I could have computed without the ciphertext. There's actually a simulator there in the definition. And in the case of decryption, we can prove that they're equivalent in some certain settings that are quite general. The analogy is clear. Indistinguishability of encryption is like witness indistinguishability, and semantic security is like zero knowledge. But in protocol, we have an implication only in one direction. Zero knowledge implied witness indistinguishability and not the other way around. So this equivalent is not valid in the case of protocols. That's something to keep in mind, even though it's very appealing as an analogy. Unlike witness hiding, both zero knowledge and WI compose. One nice thing about zero knowledge, I already mentioned it before, the fact that it leaks nothing enables us to use it as a tool without understanding what it is. It's a box. You didn't need to know the definition of zero knowledge to use zero knowledge. It's very intuitive. And Yuda mentioned the so-called zero knowledge proof of knowledge functionality. And here it is. You have a prover on the left. You have a verifier on the right. The prover feeds into the functionality a pair x, w, where w is supposed to be a witness for x being in the language. And the functionality outputs accept, says OK, if and only if xw is in the relation. This is what the zero knowledge proof of knowledge functionality gives us. It's like a black box where on one side the prover puts the witness and the statement, on the other side you get accept if and only if this is a valid witness. And you can use this black box in protocol design. And it's a special case of secure computation. Let me just spell it out explicitly to highlight the differences for those of you who know it. So the real ideal paradigm is a way to define security of protocol. It essentially said, whatever attack you have in the real world, you could have carried out equally well in the ideal world. In the ideal world, there's no attack. Go screw yourself. You don't have any attack in the real world. That's what the ideal real paradigm says. So in the context of zero knowledge, in the real world, we have a witness, a proof for X being in the language, going on. And in the ideal world, we have something indistinguishable, where you have this trusted party that attests, that agrees, tells the verifier it's all right. And now, here, no messages are exchanged, so clearly there's no attack, and this is why it's zero knowledge. The only information you get is this bit, the text is in the language. Just like we said, this is a special case of the more general notion of secure two-party computation, and I want just to mention that why is it a special case and not as general? Because as you can see, only the prover gives input to the functionality, the verifier does not. And the prover doesn't get an output, that's another difference. And the output of the verifier is just a single bit. It's not a general secure computation where you could get an arbitrary string. And indeed, zero knowledge is a special case of secure computation. These are the people involved. You can look them in the notes. And that's it.